All right, hello everyone. Thank you for the invitation. It's great to be here. As the person who introduced me just said, I'm going to be talking to you about a rather ambitious research program today, which is trying to endlessly generate increasingly complex and diverse learning environments and their solutions through this new algorithm we have called the Paired Open-Ended Trailblazer, or POET. So there's kind of a paradox in life. If you try to achieve a really, really ambitious goal, and you just myopically try to increase performance on that goal, you'll fail. But in contrast, if you kind of give up on the goal and just kind of explore the set of possibilities, you're much more likely to succeed. So there's a metaphor is this maze here. So imagine this little robot and it tries to reduce its distance to the goal. Well, it's just going to go up here and bang its head against the wall forever, which is what this optimization algorithm does when incentivized to reduce distance to the goal. In contrast, if you just kind of go out and seek out the set of possible things that are possible and explore this world, then you can ultimately succeed. And so I think that this is actually a key for all kind of innovative processes like science and technology and even natural evolution, which is you have to generate the problems while you're trying to solve them and then be willing to switch when you come up with an innovation to a different problem. So for example, if this was your current technology for heating food and you wanted to get to something that was much cleaner and faster at heating food, and you only incentivized researchers who made faster and faster ways of heating food, you would never invent the microwave because you had to have been working on radar technology, which is not for heating food at all, which ultimately gave you the microwave. And then once you built this, you might have said, oh, actually, by the way, this melted a chocolate bar in my pocket, which is what the scientists who invented this technology noticed one day, and then they started building microwaves. Similarly, if you had an abacus and you said, okay, that's pretty cool, it does computation for me. What I want is like orders of magnitude more computation, and you incentivize your researchers thousands of years ago to make better and better abacuses, then you might get more beads and longer rods, etc. But you would never invent the computer of the modern age, because to do that, you had to have gone off and invented electricity and vacuum tubes and all sorts of other things, which were essential stepping stones to make the computer, but don't immediately lead to advances in computation. Final example is coal heating furnaces. If you invested only in researchers that could produce more heat for less smoke or less carbon, then you would never have invented clean power in the form of nuclear energy, because you had to invest in this person to do researching space and time and how they interact to produce E equals mc squared and nuclear power. So the conjecture here is that the only way to solve hard problems may be to generate the problems you're trying to solve while you're solving them, and then catch chance on the wing and switch. If you're optimizing for one thing and suddenly you produce an innovation that helps with something else, then allow that thing to switch over and start being useful on a different domain. So we call this goal switching, and the idea is that if you're trying to solve one task, and if you suddenly make progress on a different task, don't throw that out as a failure. Say, hey, that's good. Now I'm going to also stop optimizing for that other task. So imagine if you have a scientist and he's trying to create a walking robot, for example, and all of a sudden your neural net that you're optimizing suddenly starts doing really well at crawling or balancing on one leg. Don't throw that out as a failure. Say, oh, that's great. Now I'm going to add those as tasks to my set, start optimizing on those too, because ultimately they might be really good stepping stones to producing a walking robot. So there's a family of algorithms my colleagues and I have been kind of creating that try to capture this property and this spirit, and they're called quality diversity algorithms. And the idea is that they're going to go off and generate a diverse set of high-quality policies that all kind of solve a task in a very different way. And there's many of them. And the one I'm going to tell you about today, because it's really conceptually simple, is map elites. And the general idea is that I choose dimensions of interest that I care about, and I discretize them. So if I have a robot, I might care about safety and fuel efficiency. I might have some other performance criteria, like how well does it drive my car, or how well does it clean my house, for example. And then what I do is I search for the best possible robot according to that performance criteria in every cell in this grid. And the result of that algorithm is not one solution that happens to have an arbitrary safety and fuel efficiency trade-off, but this kind of surface of solutions that are all different vis-a-vis those desiderata, but still solve the task as well as they can for being of that type. So you kind of illuminate this set of possibilities within the search space, and you might find out you can do really well over here and here, but not somewhere in the middle. And if you look at optimization algorithms, and we've done this over and over again, you see a qualitative difference when you use these quality diversity algorithms. So this is like a classic optimization algorithm. It doesn't do very well. We know that adding diversity helps, so you see higher performing points here, but it still doesn't really explore, even though it is being encouraged to be diverse. And map elites, in contrast, is just a sea change in terms of what you can do with the same amount of computation, which is really illuminate the entire search space and learn about the different modes that are possible out there in this search space. So interestingly, often these algorithms find a better maximum performing agent, even though they're being compared against algorithms whose only job is to find the best performing agent. And they do better, even though they're also being asked to find like the best way to do this almost impossible challenge in this top corner here. And that is because of this idea that goal switching is essential when you're trying to solve a problem. So we've looked at these algorithms, and you say, okay, here's a solution, for example, to this problem right here. And where this is the final champion point at this point. It's a really good solution for that kind of way of solving the problem. Where did its ancestors come from? Well, this map shows you the direct descendant, the parent that kind of came right before that solution. And it turned out that if you wanted to get the final best thing for this cell, you shouldn't have been working on that problem exactly, or even the problems right next to it. You had to be working on this problem all the way over here or here and leap over into search space. Sometimes you see that nearby solutions help, but sometimes very far away things are good stepping stones to ultimately the innovation that you want, because there are local optima in the search space. So you can look at an actual, not just the parent solution that produced that final solution, but the entire lineage of solutions. What problems was the history of the process working on when it finally got to this really good solution to one of these problems? And what you see is these long, circuitous, meandering paths through the search space. That if you wanted to finally solve this problem, you had to initially, all the way back, start on this problem, then switch over here, then switch over here, and walk through this totally counterintuitive, circuitous curricula to get to the final solution that you solved, which I think is really fascinating. And so we studied this phenomenon in this algorithm called innovation engines, and it started with the assumption that nature and human culture, like technology, science, and art, and quality diversity algorithms are all innovation engines because they share this very fundamental property, which is they start with a set of interesting artifacts or solutions, and then they generate perturbations on those things, and if they're interesting, they keep them and add them to the set, and they have this expanding set of interesting artifacts that are collected over time. And so one of the tasks that we tried this on is we tried Map Elites, and its job was to have a little tiny neural network generate a picture that activates the neurons in an ImageNet classifier. So each network is trying to produce one picture that makes a trained AlexNet, for example, think that that's a motorcycle or a dog. And you repeat this process for a long time. And what that allowed us to do is try optimization when you had the entire algorithm entirely focused on one class, randomly sampled, and then you do that separately for a whole bunch of classes, versus having all 1,000 classes together and allowing goal switching between these classes. And what you find is that in the single class case, you frequently run into local optima. So in this particular run, it was being optimized to produce a water tower. It landed on this motif, which doesn't look a lot like a water tower to me, and it was kind of stuck there throughout a lot of computation. In Map Elites, for example, when you have goal switching, initially it landed on this motif, which I guess kind of looks like the dome of a water tower, but it was stuck. We actually did an experiment. We ran this thing forever, and it's stuck on this motif. But eventually, an innovation from another class, which was trying to produce a beacon, came in because it kind of looked like a water tower, and then it was specialized to become more water tower-like, ultimately producing something that AlexNet really thought with 98% confidence was a water tower. And you can empirically look at this. The algorithms that have 1,000 different goals and are switching between them perform statistically significantly way better than a whole lot of separate algorithms that are each myopically focused on one task. And so if you add different numbers of objectives, you get different amounts of goal switching, and then you also get higher and higher performance, almost monotonically. So another really interesting thing about these quality diversity algorithms and nature and technology is this notion of an adaptive radiation. That you get an innovation on one problem, a new technology shows up to solve this problem, and then it can radiate out into a whole lot of different problems and be customized for each of those problems, and then further innovations can be built on the back of that. So you can kind of have these sweeps of innovations that become the foundation for future generations of technology. For example, when you have a really good fish in one lake in Africa, they can radiate out to all the other lakes, but then be specialized to those different lakes. Same with Darwin's finches, or same with computers. The initial computer was invented, and then it radiated it out into a lot of different niches throughout our lives and got customized to each of those things to be built on top of and set the stage for future innovation. And what's amazing is that you can see these exact same dynamics happen inside quality diversity algorithms. So here again is that situation where we're optimizing in little tiny networks to produce classes of ImageNet, and early on in the run there's this relatively okay abaya image, but that central motif of this dome with a colored background then kind of gets adapted to different niches over time, and ultimately that central innovation becomes the backbone for a volcano, a mosque, a water tower, a beacon, a yurt, church, dome, planetarium, obelisk, and that's dome right there. So I just think that this is a lovely demonstration of kind of an innovation that then sweeps out and then gets built upon. which is great to see in our algorithms. We also use these same ideas and technologies in this paper here in Nature on robot adaptation, where we collected ahead of time a diverse set of high-quality policies for different ways to walk. And then if the robot becomes damaged, you rapidly, with Bayesian optimization, find the best policy that works despite the damage. And so you can quickly adapt to damage in 1 to 2 minutes. I gave an entire talk at Rework on that, and that is online if you're interested. And we use the same ideas from quality diversity to tackle this extremely hard exploration challenge called Montezuma's Revenge, which has kind of almost been a mini grand challenge in deep reinforcement learning for the last 5 years, where most algorithms don't do very well on this problem at all because it's so sparse and challenging. But the idea of kind of quality diversity, like go out and seek high quality different ways to act in this game, ultimately led to this massive sea change in performance, down from maybe 10,000 points all the way up to policies that perform like 18 million and beat the human world record on this game. So QD algorithms, I think, are fantastic. They're really interesting. They produce a diverse set of high-performing agents. They harness goal switching. They conduct divergent search, which means that they fan out and try to find out what's possible within this space. So the question is, what's missing? And the answer is that they're kind of ultimately confined to the environment that you place them in. So if I'm generating images, I will only do that forever. I can't suddenly generate a house cleaning robot for you. And so the next step is to simultaneously generate the environments that they're working in as opposed to keeping them trapped. And so that's why we're interested in these algorithms called open-ended algorithms, where they just endlessly innovate. You turn them on, and forever they just keep producing innovative solutions. So if you think about natural evolution, for example, it's been running for over 1 billion years. And look at all of these endless surprises it produced in the tree of life. Somewhere in there are jaguars, hawks, and the human brain, and it's still going. So the question is, what algorithms could we create that we would want to literally give 1 billion years of compute to and come back and still find that they're interesting? And we don't have those yet, and I think it's interesting to try to build them. So in traditional machine learning, we pick a task and then we try to solve it. These algorithms, in contrast, would generate the problems while they're also trying to solve those problems. Just as in nature arguably generated the problem of leaves high up in trees, and then the solution, which might be a giraffe or a caterpillar that can go eat those leaves, for example. So again, can we create an algorithm that's interesting after 1 billion years? So our most recent approach here is the Paired Open-Ended Trailblazer, or POET. And this algorithm endlessly generates increasingly complex and diverse learning environments and their solutions. The idea is that you periodically generate new learning environments and you add them to the population of environments if they're not too easy and not too hard, and if they're novel. And then you optimize agents to better solve each one, and you allow goal switching. The task here is this little robot that basically has to walk without falling over, and it has a set of sensors. We're going to have these obstacles: stumps, gaps, steps, and roughness that we can add to the environment. And so here's how it works. You start with a parameter vector phi that initially specifies an environment, and then you optimize this theta in this environment. You generate a new environment at some point. And then you'll transfer the skills from this agent in by copying this weight vector and optimizing this on this environment and simultaneously optimizing this on this. We might try to generate a new environment that might be too hard for any of the current agents, so we try again. We get this environment. We try both of these to see what's the best parent to start this optimization process, drop that in, start optimizing on this environment. And it doesn't have to be linear. This thing is kind of expanding out in this set of environments that it's optimizing all in parallel. And we allow goal switching to figure out at any point something could switch from one problem to the next. So imagine eventually you generate this extremely hard problem here. Initially, it seems like theta 5 is the best starting point, so you optimize that for it. But because we allow goal switching, this might get stuck on a local optima. This thing may end up being a better stepping stone to ultimately doing better in that problem, and then it may end up being the best stepping stone to come in and get off of a local optima and solve that problem. So there's a 3-layer neural network that we're optimizing with ES, but it could be any RL algorithm, but this one was easy to distribute. So here we go. It starts off easy with this little agent that's kind of on simple problems with not that rough terrain, little tiny stumps, little tiny gaps, and it's kind of slowly figuring out how to solve each of these problems separately. Here's some rough grass. And over time, the problems are going to start to get more and more complex because we're randomly changing environments and creating ones that are not too easy and not too hard. So now this agent has mid-level gaps or really tall stumps, but it hasn't seen them in combination. It's kind of separately working on these challenges. This is all organic organic within the algorithm. And then after it kind of learns to do this medium difficulty tasks, it'll end up getting combinations where it's simultaneously being asked to solve really large gaps, really tall stumps, really rough terrain, all at the same time. And it can kind of use its sensors to like run up and leap over these chasms to the best of its ability, and it learns how to do all of that. Here's another challenge that we were really surprised to see. We didn't think that was even possible in this world, but there it is. So we ended up classifying these things according to their difficulty so we could do some analysis. And if you take relatively challenging environments that Poet can solve quite well, and you directly optimize an agent from scratch in that environment, it totally fails. And you might not be surprised because there's no curriculum. So you might do something else and say, let's pick these environments here and create kind of a direct path, a direct path curriculum, which has kind of a linear interpolation between this environment, and then has stepping stones along the way. This is a very common idea you see frequently in RL. That also doesn't work. Basically, at some point in time, as long as there's one weak link in this chain, then the entire process grinds to a halt, and there's no backup plan. And so what we see is that the more hard challenging the problem is, the further away it gets from accomplishing its goal over and over and over again. What you need is instead is to kind of simultaneously be investigating multiple different curricula through the environment and hedging your bets. Ultimately, one might win, but you don't have to know ahead of time what is the best path to get there. So I want to give you an example of this in practice. Here is a very simple environment, and you have this agent that learned how to walk while dragging its knee. Ultimately, it will the environment gets copied, and now there is this stump here. And now this knee dragging behavior doesn't work. So this agent with more optimization learns to stand up. And then because we're always doing goal switching and checking, it turns out this is a nice stepping stone to go back to the simpler environment and stand up and get a higher performance. And with further optimization in this environment, you get this really nice score of 350. And we did the counterfactual, where if you just give this thing lots more computation, it gets stuck. It never picks its knee off the ground, and it gets there at 309. So here's a nice example of it. Goal switching is needed to solve the hardest challenges in this domain. If you do Poet without goal switching, you never get the most challenging versions of the problem. So there's plenty of related work here. See our paper for the full list and references. I just want to quickly tell you about future work and then conclude. So one thing obviously we'd like to do is try this in more complex environments, like those that are in these nice 3D environments here. I also think it's interesting to do multi-agent interactions. So the agents themselves, different combinations of agents, can be different challenges that you're trying to solve, and you could learn these very, very complicated tasks. But I really think it's provoking to put up an environment like this. Imagine what such an algorithm would do in this rich of an environment where there's all sorts of different things you can learn, interacting with different tradespeople at the market, or avoiding birds, or climbing this building here, and exploring swimming worlds and canopy worlds, and fighting scenes and cooperative scenes. It's just a rich, rich space in which these algorithms could diverge if they had enough compute. Another interesting direction is to simultaneously optimize the body as well as the agent. David Ha has done that in this environment. Here's some soft robotic work that I did years ago. But you could imagine these things learning to squeeze through keyholes and climb under tables and rocks if you gave it sufficiently complex environment. I also think it's interesting to simultaneously generate the reward as well as the environment. Obviously, if you give this more compute, these algorithms are really nice because they could potentially just generate more and more solutions and discoveries and skills and innovation with lots and lots of more compute, which is fascinating. Also, in a meta-learning context, meta-learning right now requires a distribution of tasks, which is usually hand-designed. Poet could generate all these atomic tasks, and you could add those to a distribution that a meta-learning algorithm could then learn on. And what's nice about that is then instead of getting a whole lot of different specialists that each solve each task separately, now you get a generalist that can solve as many of those tasks as possible, which is kind of fascinating. Whoa. So a final thing I'll just mention is that ultimately I think this might be a stepping stone to getting to really ambitious AI goals in terms of creating AI-generating algorithms. So if you simultaneously generate the learning problems, and you meta-learn the learning algorithms themselves, and you meta-learn the architectures, now you have an algorithm that might be able to bootstrap itself up from very, very simple all the way to maybe even general intelligence. That has an expensive outer loop, but is ultimately producing something on the inner loop that is very sample efficient and intelligent. And we know that works because it happened on Earth, which is quite fascinating. So to conclude, automatically generating environments and their solution, which is what Poet does, is a very interesting idea, I think, because it invents its own curricula. It It creates and collects stepping stones. It harnesses goal switching. The curricula are often very counterintuitive. In the example I showed you, had to go to a harder problem, work on that for a while to ultimately come back and solve a simpler problem, which no learning algorithm or human design system would typically do on its own. And it hedges its bets with multiple overlapping curricula. It also endlessly innovates, and therefore may be the only way to solve really ambitious problems and discover the full gamut of what is possible in a search space. And it also tends to capture the open-ended spirit of innovation engines like natural evolution and cultural evolution, like science, technology, and art. And it finally, as I mentioned, opens up a lot of fascinating future research directions that we think are really interesting to pursue. And we're also interested to see what this community does with these ideas woven into your algorithms. So with that, if you're interested in more, we put a whole tutorial at ICML 2019 on these subjects online a few days ago. And I want to thank my co-authors and all of you for listening. Thanks.